Welcome back. I'm done with chapter 3, or with everything I'm covering from chapter 3 myself. There is more material on Silverman's book, which I recommend people read on their own about the invariant differential, about the endomorphism ring, about the automorphisms of an elliptic curve. But I need to pick and choose my battles for this class. I'm going to actually jump from chapter 3 to chapter 5, I believe this is, in Silverman, because, well, I feel like, because I'm going to talk very little about finite fields, unfortunately, and if I leave it for later, sort of like breaks the monologue, my monologue about elliptic curves. We're going to, once we start with formal groups, it's going to be really convenient to go directly into local fields and then directly into the proof of the Mordell-Weil theorem. So let's talk a little bit about curves over finite fields. Very briefly, unfortunately, there's also some beautiful stuff in this chapter about the Weil conjectures that I also recommend that you read on your own, which is a fascinating topic. But also not until like much later we would actually use the zeta function of an elliptic curve to define the L function of an elliptic curve. So we are going to, for now, just very briefly talk about finite fields and elliptic curves over finite fields. What I do want to say, what I do want to talk about and prove is one of the most important theorems in over finite fields, which is the Hasse bound. So let's go for it. So here's the question. So let K be a finite field. Whoops, typo. So let K be a finite field with Q equals P to the n elements, where here P is a prime. Every finite field is of this form. So it's always one of these. You take a prime. You can think about, for example, FP. So for example, you've at least probably have seen FP, which is just Z mod PZ. And if you want to construct a finite field with P to the n elements, then what you can take is let f of x be a polynomial over fp that is irreducible of degree n, and build k to be fpx modulo f of x, and that will be a field, and is a field extension of degree n over fp, which is of p to the n elements. Okay, so for example, if you take, let's say, p equals p equals 3, then the number 2 is not a square, so x squared minus 2 is irreducible over f3, and therefore you can construct k to be f3 x modulo x squared minus 2, and basically adjoining a square root of 2 to build is a field with 9 elements. Okay, so here are finite fields. All right, so now I want to define elliptic curves over finite fields. They are defined exactly the same way we define elliptic curves over any other field. So now I do want to have fields, for example, the example above of characteristic 3, characteristic 2, of 3 to the n elements, 2 to the n elements. So I need a full Weierstrass form to define my elliptic curve. So, so this elliptic curve is going to be given by something like this. With AIs and in K, and such that it's smooth. Okay, so I want the discriminant to be not 0 in K. All right, so so here's a question. The question is going to be, so now we are working over a finite field. There's only finitely many possibilities for X. There's only finitely many possibilities for Y. So I can actually count how many points are there in EK, in the points defined over K. I can actually compute directly all the points on an elliptic curve or finite field just by brute force, essentially. So what are the number, how many points are there on E over K? I can later ask more refined questions such as what is the structure of this group? Is an abelian group, is a finite abelian group now, and I can ask what is the structure of it and so on. Those are more refined questions. So let me try to answer that question. So let's just do a few heuristics first of all. Well, first of all, as I said, I know it's a finite number because the points defined over K are going to be inside, well, K cross K, right? Union the point at infinity. There's still, even over a finite field, there's only one point at infinity that I'm not missing if I go through all the points in K, all the possible coordinates X, all the possible coordinates Y, that's K cross K, and the point at infinity. So that's that many, and then this directly implies that the number of points, well, it cannot be more than Q times Q, so Q squared plus 1. So that already gives me a very rough bound that the number of points is at most Q squared plus 1. Right. I can do better than that because for each value of X, what happens? Look at the Weierstrass equation. As I pick a value of X, now the values of Y is a quadratic in Y, right? So for each value of X, there are at most 2 possible values for Y. We're working over a field, okay? And over a field, we have a theorem that says that, well, over a field, a polynomial of degree 2 has at most 2 roots over a field with multiplicity. So I have at most 2 values of Y there. And what this tells me is that the number of points is at most, for every value of X, Q choices times 2 values of Y. So it's at most 2Q plus 1. Okay. Can I do better than that? Well, yeah, because, well, not provably. Now, here's where we're going to get a little bit heuristic-y, is that for every value of X, I can look at the polynomial in Y, that's a quadratic, and there will be points. So there are 2 values, or there is actually one value, only one value, if there are most 2 possible values. So let delta be the discriminant of that polynomial in Y. One value if the discriminant is 0, 2 values if the discriminant is a square. okay? But there is exactly half of all the points on K cross are squares, okay? So this is a fact for you to prove. If you don't know that, is that the number of squares in a finite field will be Q minus 1 divided by 2, right? Because there's Q elements minus 0, and then half of them are squares. There's Q minus 1 divided by 2. So what that tells me, and this is now conjecturally, is that the number of points will be approximately, there will be for every x, let's say at random, it should be random whether the discriminant is a square or not. So for half of the values of x, I get that I have 2 solutions, and for half of them, I don't have any solutions. So this is going to be for half of the values of x, for q minus 1 over 2, there are 2 solutions, okay? And then there is O. Did that work? No, because there is also what happens with 0. Okay, there will be also when x, when delta is 0. So there is that, whether there is only one solution when x is 0, and when the discriminant is 0, and then plus 1. So this will be, in total, I get q minus 1 plus 1 plus 1. That is q plus 1 points. And this is actually not a bound. It should be approximately q plus 1. Okay. Yeah. So this is actually Hasse's, this is a conjecture of Artin that there should be approximately q plus 1 points. And Hasse proved this. So here's a theorem, which is usually called Hasse's bound. So this was conjectured by Artin, and then proved by Helmut Hasse in the 1930s. And it says that the number of points on an elliptic curve or a finite field minus q minus 1, so compared to q plus 1, is actually bounded by 2 times the square root of q. Okay, so it tells you that, yeah, it's approximately q plus 1 with an error of twice the square root of q. Okay, which is significantly smaller than q. Okay, so here's a proof, and I have not proved all the pieces that we need for this, but I'm just gonna call in some of the things that we actually need from chapter 3 to prove this. So first ingredient is actually, it appears in corollary on chapter 3.6.3, and is the following. So let E, E2, E1, and E2 be elliptic curves. Then the degree map, of a homomorphism from E1 to E2 to Z, it turns out, is a positive definite quadratic form. Okay. So what does this mean? A quadratic form means that we have a map from an abelian group A to R, such that D of alpha is D of minus alpha always, and such that if you do the map from A cross A to R, which is the pairing that sends alpha beta to degree of alpha plus beta minus degree of alpha minus degree of beta, this is bilinear. Okay. And also that D of alpha is bigger or equal to 0, and D of alpha is 0 if and only if alpha is 0. This is what we say that this is positive definite. Okay. So that degree map from Homs to the integers is a positive definite quadratic form. Great. Now, another piece that I have not discussed so far is the Frobenius homomorphism. So when you are defined over a finite field, there is an extra endomorphism, which is the following. It sends xy to x to the q, comma y to the q. Okay, where here k is a field of q elements. Okay, this is the Frobenius endomorphism, and it works. It goes from E to E because the coefficients are over k. The coefficients of E are defined over k, and that implies that AI to the q equals AI. Okay, that is a property that actually defines finite fields. The finite field of size q are all the roots of the polynomial x to the q equals x. Okay, so the points, the numbers that are in k, they satisfy that property. Okay, so if you have something that is in k, raise it to the qth power, you get the number back. If you think about this in the case when this should be familiar, at least when q equals p, this is Fermat's little theorem, right? Great. And it turns out the degree of phi is q. Well, you see that is a map of degree q, and then what we can do is the following. So now consider let's rewrite maybe here the endomorphism. This is the Frobenius again. I can write the points over k, I can write them as the kernel of the identity minus Frobenius. Okay, this is because if a point is defined over k, then this is equivalent to Frobenius acting trivially on p. Again, the coordinates that are in K are exactly the numbers that when you raise it to the qth power, you get the same number. Okay, so if you have that, then Frobenius acts trivially, and if it acts trivially, then it's because the coordinates are in K. So this condition is the same as phi on a point is the identity on a point. So the identity minus Frobenius on a point gives me O. So the points on K are the kernel of the map identity. If you want, just write it identity like this, minus Frobenius. That is a map, so I can actually compute then the number of points on my map, on my kernel, the number of points on a kernel of an isogeny. We know how to do that now. That is the degree of the isogeny. So it's a matter now of computing the degree of this isogeny, identity minus Frobenius. So the theorem will follow. Oops. If I can bound this quantity, which is the same as the degree of the identity minus phi minus the degree of 1 of the identity minus the degree of phi. Okay, so if I can bound that, then I can bound what I wanted, which is the difference between the number of points over K and 1 minus Q. Great. So it turns out that this is something that is a little bit more general for any positive quadratic form, positive definite quadratic form. There is a bound, there is a known bound for this quantity. So this is now just a lemma about quadratic forms. So let A be an abelian group. And suppose that D from A to the integers is a positive definite quadratic form. Then for all elements psi and phi in A, we have that the value of d of psi minus phi minus d of psi minus d of phi, which is a natural quantity to compare what is d of a sum or a difference with a sum of the d's, that it turns out to be less or equal to 2 times the square root of d of phi, d of psi. Okay, so here's a proof of this fact. And notice that now we are done. If we apply this to what we want, this would be less or equal to 2 times the square root of d of the identity, which is 1, times q, which is 2 root q, which is Hasse's theorem. Okay, so here's the proof. So you let an auxiliary function L of psi and phi is going to be this difference of the values of the quadratic form. Okay, which notice that this is bilinear because D is a quadratic form. That is the form that is bilinear by definition of a quadratic form. You see before, here it is. That's part of the definition of quadratic form. That has to be bilinear. Perfect. So this is bilinear. And now from the fact that is positive definite, we have, we want to compute d of any combination of psi and phi. It turns out, if you write, I can write this in another way, which is m squared d of c plus m n l of psi phi plus n squared d of phi. If you start from the right-hand side, if you start just expand that by linearly, then you'll see that, so expand that by putting the m here and the n there, then you'll see that if you add those two together, then you would get this one as a result. Okay, so this is always positive, and now take, this is for any m and n. I'm going to take m to be minus L of psi phi, and I'm going to take n to be 2 times d of psi, and this yields that 0 is less or equal to d of psi times 4 d of psi d of phi minus L psi phi squared. Okay, I'm going to do it out, but if you put in that m and that value of n, it turns out this is what it comes out. And if you just take any psi that is non-zero, so that the value, so that this value is positive, for this to be positive, then this has to be positive, and therefore, therefore the value of L psi phi in absolute value, that has to be less or equal to the square root of the other term for d psi d phi, as we wanted. And that concludes the proof of the lemma, and it concludes the proof of Hasse's theorem because of that inequality. That is an outcome of the lemma. Okay. So as I said, this is all I'm going to need, and I'm going to prove for elliptic curves over finite fields. There's a whole world out there of theory of elliptic curves over finite fields, because it's very useful in applications, for example, to cryptography. An elliptic curve over finite fields. There is in the second edition of Silverman, there is a chapter on sort of computational aspects of elliptic curves, and in particular, there's a discussion of elliptic curve cryptography there, the elliptic Diffie-Hellman algorithm, and so on. So there is a lot of research about elliptic curves over finite fields, but in this course, we're not going to get into any more aspects of finite fields. So we'll continue next time. I'm actually going to jump around again a little bit, and I'm going to talk also very briefly about elliptic curves over the complex numbers, so it's chapter 6, and then we'll go back and talk about formal groups. So we are ready to talk about elliptic curves over local fields. All right, until next time.